back to the notes. Anybody who is ready got it? If not, you know where to find it. Google Classroom. No big deal. And for those of you guys curious what the schedule is today, where are we at right now? Period 3? I guess you don't need the beginning ones. We have P3, then period 4, then nutrition. You guys have one more period before your nutrition. Then 5, then 6, then 7. Period 3 is 9, 10 to 9. Then 9. Huh? Oh, open it, yeah. As I said, what happened to it? I was like, I don't know. It looks good. Just throw that doorstop in. Can't have to jam it. Then Nathan, we're still good for test? Sure. Try to flip it the other way. The ridges in the bottom work a little bit better. I know it's a mess. There you go. You got it. Alright, cool kids. So, minimum schedule is on the board. Homework is, well, we usually talk about what we're doing today. We're finishing 3.1 with our homework due on Monday. Last chapter. The one you just took a test on, most of you. Algebraic functions. This chapter, transcendental force. Say more to you about the transcendental words and the exponential logarithmic. We're transcending. Doesn't that sound exciting?
No.
You want to die. No. Okay, what I want you to think for this entire chapter 3, I'm going to make this quick, is puzzles. And out of any class I've ever had, you guys should rock this chapter. Why? What do you do almost every day like the majority of you? Puzzles and talk. Puzzles and talk. So, my puzzlers, this chapter's for you. But the dilemma is, if you wanted to play like a logic game, or a brain game, or a puzzle game, don't you kind of have to know what you're supposed to do yet? Or first, right? For instance, what's it called? Canoodle? The one that Nathaniel is addicted to. What if you just had pieces? That's it, just the pieces. You didn't have the little patterns. Yes, I stole them from him. You didn't have the patterns. I mean, I guess you could make your own. I mean, Nathaniel made his own, like 2 extra ones that aren't in the book. He was like, sure, why not? But, coming back, would that be as fun for most of you? No, because you're like, well, what's the objective? What's the point? What's the goal? What am I supposed to do? And, okay, most of you know how to do it. You're like, okay, I'm supposed to fit them together somehow, right? But without some sort of objective or goal, it's not as fun. You're not, like, meeting the desired end. Sudoku. I put it up on the board the other day, or a few times this year. How many of you just looked at it and said, oh, yeah, I never knew how to play that? So did you play it if you didn't know how to play it? If your parents were playing it, you just start filling in random numbers and saying, yay, look, I did a good job. It's no fun if you can't win. Come on, my athletes, right? It's no fun if you can't win. True?
Not Joe.
What if you just go out and, like, I don't know, let's just say you were tiny, you went out and there's like a net, there's a couple poles, a few volleyballs, and you're like, okay, what's the point? If you didn't know how to play volleyball, what's the point? Now, maybe you would figure out to put up the net and then something about throwing the ball over. Basketball's a little bit easier. You see a hoop and you see a ball and you're like, I think it's supposed to go in. But even then, right? Until you learn the technical parts to the game, or until you learn how to build your skills, like, it's only going to be so fun for most of us, right? This chapter is all about learning the rules to meet the objective, and they're all going to be in some way, shape, or form once we get to section 2, 4, 2, 5, 2, 6. I forget how many sections are in this chapter. Sorry, 3, 4, 3, 5. You're not going to necessarily see the full picture. The beginning is just learning the rules, learning the technical parts, learning the different things we can do, the moves we can make that are legal. And then we're given a problem that's like a big old puzzle and say, hey, figure this out from all of these parts. Now, maybe that sounds lame to you, but to be honest, these can be really fun, but you have to learn the rules first. And if you don't learn the rules, what are you going to be when you get to the puzzles at the end? Frustrated, annoyed, and doing illegal math, aka getting it wrong and getting a low score. You have to learn the rules first. So, these first two sections are literally just introducing the players. What you're going to see at the end, you're going to see puzzles that have exponentials and puzzles that have logs. And if you don't know who they are, you're like, well, I have no clue. So 3-1 introduces exponentials, 3-2 introduces logs, and then we start going with, okay, what can we do? 3.1, exponential function. I don't know, maybe like 5 or 6. That's what I was trying to remember. Standard form. All right, this guy. One key category, exponential functions. Who are the pieces? Who are the players? What are the parts? We first have a base, and we have an exponent. The base is always a constant. It's always a number. The exponent is always a variable expression. I'm putting variable expression because it could just be a variable like x, or it could be like x plus 2 or x squared minus 1. It could be more complicated. But exponential guys, they always have a constant that's down and a variable expression that's up. Now this part just says, can you use your calculator? I don't know. How do we plug in negative 3.1 to 2 to that? Because we just need 2 to the negative 3.1. How do we do that? I'm literally just checking you know how to use your calculator. How do you get it to go up? Caret. Caret. Yeah, just use the up caret, right? What should this be? 8-ish. Because 2 times 2 times 2. 2 cubed is 8, right? 8-ish. Wrong. Negative 8-ish? Wrong. 1 over 8-ish, because negative coefficients, negative exponents pop it down. I'm just working on your mental math a little bit. 2 to the 3, 2 cubed is 8. 8-ish? No. 1 over 8-ish. Remember, negative exponents pop it down, but I did tell you just to plug it into your calculator. Has anyone proven they know how to use their caret button? What do you guys got? I think it's like 0.125-ish. 8.57. What was it? 8.57? 0.116? Is that what it says, right?
No, it's 1 over.
It's 2 to the negative 3.1, which is 1 divided by 2 to the 3.1.
Yeah, 2 to the negative 3.1 is 1.16, but 2 to the just 3.1, because 2 to 3.1 is 8.56.
So should we, when you want us to solve it,
is it 1.16 raised to like e to the negative 1?
No, like what he's saying is like 2 to the 3.1 is
8-ish.
Yeah, 8-ish.
And 1 divided by 8-ish is
2 to the negative 3.1 is 3.16.
I was hearing 1.
But then 2 to the 3.1 is.
Got it. Sorry. 0.116. 0.116. Okay. So what's going to happen when we do the second one, where it's 2 to the negative pi? Wait, why are we plugging in pi? Because pi is a number. Isn't it going to be about the same? 1 over 2 to the pi. Pi is just a constant. It's not pi day yet, but pi is just a constant. Wait. Why was it so close to the other one? Oh, because pi is 3.141, but anyway, that was random, but there you go. Okay, the caret button in your calculator raises it to a power. If you're raising a whole base to a negative number, it's going to be a small value because it's 1 over. Exponential functions, they go, there it is. Algebra 1 did it just a little while ago. Exponential growth and decay. Exponential growth and decay. A basic exponential graph. Now in honors, we talked a lot about the different behaviors and what can change and what can happen. Went to our calculators a lot, talked about chemistry and half-lives and doubling. But for us, swoop, there it is. Okay, this is a basic a to the x graph. But guys, there are some a's that won't behave like this. Maybe some of you can think about it. I can't give you a lot of time, but can you think of any a's that wouldn't work like this? Why not negatives? Now, careful. The negative number would need to be inside, not a negative on the outside. A negative on the outside would just flip it, which it would be different. But a negative on the inside wouldn't even be a swoop. Why? What would happen if I did negative 2 to the 1, negative 2 to the 2, negative 2 to the 3? Is it still getting bigger? Yes, but what's happening to the signs? Positive, negative, positive, negative, positive, negative. Oh, it's a mess. It's not a nice clean swoop. So I need A to be greater than 0. Wait, why greater than? Why not 0? What's wrong with 0 to any power? Oh, that would just be a flat line. Well, forget that. That's no swoop. What's the other one number that wouldn't work? 0 causes a flat line. Negatives cause this oscillating, mumble-jumbled confusion. 1. Good. What's 1 to any power? Oh, that doesn't work. 1 to any power is 1. That's a flat line. So 1 isn't going to swoop. 0 is not going to swoop. And negatives are, well, infinitely confused. So they don't work either. But any other base, a.k.a. any non-1 positive base, is going to swoop. There it is. Well, almost any base. What if A is within, remember our little intervals? What if A is within 0 to 1? Not 0, not 1, but why did I not just say greater than 1? Why did I leave out 1/2, 2/3, 3/4, 5/6? Well, because they can still swoop, but they're going to swoop differently. Do you guys know what happens when I square 1/2? 1/2 times 1/2 is 1/4. What if I cube 1/2? Oh, we just talked about that. 1 over 2 cubed is 1 over 8. How about 2 to the negative 4, 1/2 to the 4th? Wouldn't that be 1/16? What's happening to numbers as the little fraction gets raised to higher powers? These guys are going to be swooping just the other way. They don't even need a negative. They don't even need a reflection. 1/2, 1/3, 2/4. That's awkward. That's 1/2. 2/3, 5/6, 9/12, 99 100ths is going to be swooping there. Anything that's in between 0 and 1 raised to higher powers decreases. But anything greater than 1 will increase. Domain, all real numbers. No problem. Forever left, forever right. Not a point. Remember intervals. Range. Oh, that's not good. Range is 0 to infinity. And not hitting 0 because I have a horizontal asymptote, right? Oh yeah, horizontal asymptote at y equals 0. My y-intercept is always going to be 0, 1 of any non-transformed exponential because anything to the 0 power is 1. Well, except for 0 to the 0, but he's not included. He's actually undefined. It's a snazzy thing called indeterminate. What else? Oh, strictly monotonic. You might be like, what on earth is going on there? It's strictly moving one direction. Not the boy band, but it's strictly moving one way. It's only increasing. Sometimes slower, sometimes faster. It takes all of negative infinity to 0 to increase quickly, but sometimes slower, sometimes faster, but it's always going to be going up. That's what that means. Monotonic, monotone, one tone, one behavior. Continuous. No breaks, no holes, no vertical asymptotes inside. So if I say, great, that's the parent function, that's the basic dude, then what do you know is coming? The transform. That's the basic dude. Well, okay, now we can transform it. Now, in some ways, I'm going to fill all this in green because it's kind of review. Now, sorry, this guy's kind of light and kind of small. Let's see if I can. Why are you writing? Huh. Let me see if I can make this guy a bit bigger. Can you see him a little bit better? If you have something added on the outside of an exponential function, it's going to be a shift up and down like it always is. Just exponential functions are a little bit to get used to as far as where the outside of him is and where the inside is in his exponent. So if I'm subtracting, adding on the inside is going to be a horizontal shift. So I have a vertical shift adding on the outside, horizontal shift adding or subtracting on the inside. If my bases change, my bases affect, you could say like the shrink and stretch. Not to say you can't have dilations, like you can have like 2 times like an exponential or 1/2 times an exponential or a negative times an exponential. You can still have dilations, they're just not as common. But what you'll see more is like 2 to the, 4 to the, 5 to the, 2/3 to the, and all of those different bases kind of make it steeper or make it less steep or flip it. Like we saw over here, those little fractions will flip. Across the x-axis, horizontal. Oh wait, this was a horizontal flip. I wonder if it has anything to do with this. Horizontal flip, wouldn't that be, oh wait, x-axis, that's this guy. Horizontal flip, wouldn't that be putting a negative in the exponent? An inside negative? But wouldn't that be the same thing as flipping, which is the same thing as, so when you see a 1/2 or when you see some little fraction raised to the x, it's really a negative exponent. No wonder it flips horizontally. Remember, that's our horizontal flip. Across the x-axis would be that negative on the outside. Careful, that's a negative a to the x, which is why it's legal. I'm not raising that negative to the x power. I shouldn't have that in the parentheses. The negative is technically outside due to PEMDAS. Just in case a few of you are like, wait a minute, you said no negatives. No negatives inside the base. But this would be a negative on the outside. That's a vertical flip. But anyway, transformations, that's a thing. That can happen. So what if we do a couple examples? E, who the heck is that guy? Where did he come from? Why is he showing up in this section? Oh, hey, he's in your calculator. Do you guys see that E is right above ln? Second ln gets you an E. I wonder if they're related. Second log gets you a 10. I wonder if they're related. Interesting. But there's also another button for E somewhere. There's like an E to the 1 and an E to the x. Anyway, E, if you guys put him in your calculator and do E to the 1, it's 2.71828. Oh, actually, I think I have some notes on him. Never mind, I don't have notes on him. I thought I did. He's called the natural number. Oh, there he is. Let's pull him up. If you see E, don't be confused. You go to your calculator and plug him in. He happens a lot. 718281828. There's a pattern. Oh, stink. That's what he is approximately. Love computers when they don't like you. Life is sad. Just kidding. Have some good even for yourself. But E is the natural number. That's literally just his little name. Kind of like pi. He does have a decimal. He does have a decimal with a repeating pattern, so he's a little bit different than pi in that way. But we'll get back to what's going on algebraically here. For right now, that just means when we go to graph, well, hold on. Every exponential function has an intercept of 0, 1. That's easy. But here's something else you should keep in mind. Every exponential function also has the point of whatever the base is with 1. Meaning, if I plug in 0, any exponential function is 1. If I plug in 1, any exponential function is its base. If I plug in 1, I'm going to get 2.71828. So I also have the point 1e. And then 2. So if I was to do the red one, if I was to do a vertical shift up 3, you're tracking, right? It'd be nice to be able to go 1, 2, and 3 to move that point up to go, well, 1-ish, 2-ish, 3-ish. He's a little awkward. He's going to be in a 0.7 spot. But guess what else is going to be really helpful? With swoops, we don't just need a couple points. We also need to shift. Who else is there? And if we shift the asymptote, it makes it so much easier to graph. We shift it up 1, up 2, up 3. Now all of a sudden it's like, oh, that's easy. Shift the 2 key points, 0, 1, and the base. 1, comma, the base. But when we get to like letter H, we have 2 reflections. We have a vertical flip and a horizontal flip. Well, we're going to have to flip this guy. Well, he doesn't go anywhere horizontally, but flip him vertically. Got it. Flip this guy horizontally and vertically. Got him. But does anything change with the horizontal asymptote if I'm just flipping and flipping? There's no vertical or horizontal shift. It's going to be just fine. And maybe some of you realize if there's no horizontal shift, or sorry, if there is a horizontal shift, it's not going to make a difference either. Anyway, my advice for graphing transformed exponential functions is to use the key points 0, 1, and 1a, and the horizontal asymptote. Now guys, I know we started talking about this little e guy, and that was good and all, but really for homework, the other thing you need to see before we leave is the one-to-one property that allows you to solve equations. Because the one-to-one property says, you know what, back from Algebra 1, it's just review. Back from Algebra 1, this is so hard to solve unless you can make the bases, anybody know what 64 is? 2 to the power of, sorry, if you can make the bases match, guess what you get to do according to this really cool one-to-one property? You just ignore them. Technically is what the one-to-one property says. If these two are equal and the bases match, you just go for it. So therefore, don't we know that x is equal to 3? Just make the bases match. So that's not my Algebra 1 kids. Why is this just a little bit harder? What do we do when we're given fractions? Negative. Negative exponent. So maybe you'll have to do some factoring trees. Maybe it'll take you just a little bit, but if you can make the bases match, you're golden. Make the bases match, set them equal, you're done. Woo! We got it! End of section 3.1. See you guys later. Period 4 before nutrition. Awesome job. Way to rock it. Nathaniel, give me your notes.